My name is Wang Yiwei. I am a PhD student at the National University of Singapore. The paper I will be presenting today is Graph Explicit Neural Networks, explicitly encoding graphs for efficient and accurate inference. Inference efficiency and accuracy are two popular criteria to evaluate a machine learning system. Nowadays, growing demands of graph learning applications in the industry necessitate models which infer with low latency. Besides, the increasing privacy-preserving services pose accuracy challenges to graph learning systems under limited feature constraints. Yet, state-of-the-art graph learning models, message passing neural networks, MPNNs, struggle in these latency and feature constraint settings. Graph topology and node features are two main sources of information for graph learning. The former is irregular and discrete, while the latter is regular and continuous, making the latter more conveniently encoded by neural networks. Given these data characteristics, MPN message passing neural networks explicitly encode the node features but implicitly uses the graph topology as pathways to propagate node features. We argue that the way message passing neural networks implicitly use graph topology creates these seemingly disparate but ultimately coupled fundamental limitations: over-reliance on node features and slow inference. These disadvantages reduce the applicability of message passing neural networks for inference in large-scale industry applications. Because the graph topology is only implicitly used by message passing neural networks as pathways for fetching the neighbor's features. If the node features are not informative, graph topology has no valuable information to convey. We find that the low feature settings severely degrade the message passing neural network's performance and hurt their practicality. This phenomenon is consistent across various graph benchmarks and implies that message passing neural networks rely on the informative node features for accurate predictions. In many industrial services, the model only have limited access to node features for reasons of privacy, fairness, or availability, where over-reliance on features can lead to serious degradation of effectiveness. The implicit use of graph topology forces message passing neural networks to propagate the features over the edges. In other words, message passing neural networks have to fetch and transform the high-dimensional representations of many neighbors to expand the receptive fields on the graph topology. As a result, the prediction on a single node of message passing neural networks requires many neighbors feature lookups as well as multiplication and accumulation operations, and thus causes high inference latency. This makes the message passing neural networks challenging to deploy for latency-constrained applications which require fast inference. This issue is also known as neighbor explosion when the number of layers is high. Because message passing neural networks' implicit use of graph topology induces both these issues, we aim to explicitly utilize the information from graph topology to address them and improve message passing neural networks. However, graph topology is irregular and discrete, which makes it non-trivial to handle with an MLP. To process the graph topology, we utilize the recently developed method, instant embedding, from a classical domain of graph learning, network embeddings, to transform the irregular graph topology into regular node-level embeddings. Instant embedding is efficient and inductive, which forms our basis for quickly prioritizing the graph topology for inference. On the other hand, when the node features are rich, message passing neural networks are still the most effective graph learning models. Therefore, in our work, we propose a knowledge distillation-based graph neural network framework, Graph Explicit Neural Network, to improve message passing neural networks for the efficient and accurate inference that is robust to the feature-constrained settings. Graph Explicit Neural Networks takes a message passing neural network model as the teacher model during training, but avoids using it for inference, so that we can benefit from the distilled knowledge of message passing neural networks while avoiding their high inference latency. We use the message passing neural network teacher to supervise instant embedding as the student model for fast inference and enjoy the enhanced effectiveness from the teacher. However, instant embedding is parameterized and thus cannot be supervised by message passing neural networks directly. To transform the output of instant embedding in the direction that adapts to the message passing neural network teachers, we propose the topology student module that constructs a multi-layer perception upon instant embedding. The distilled topology student augments the instant embedding's outputs for higher effectiveness. In this way, we explicitly encode the graph topology as an important source of information for inference, so as to mitigate the over-reliance on the node features. Given our topology student that explicitly encodes the graph topology, there still exists the possibility for higher effectiveness by utilizing the node features. Therefore, we propose an MLP-based feature student module to encode the input node features under the guidance of the message passing neural network teacher as well. To fuse the information in graph topology and features, one practical obstacle is that the correlation between the graph data and the ground truth labels is very complex. The labels can be more correlated with either graph topology or features, depending on the instance. In order to extract the most relevant information from graph topology and features, we utilize an attention-based fusion head to learn importance weights for our student modules, so as to fuse the graph topology and features in an adaptive and interpretable manner. During inference, graph explicit neural network makes the predictions by fusing the outputs of two student modules, avoiding any neighbor feature fetching or transformation, unlike message passing neural networks. The inference of graph explicit neural networks only includes two efficient students and a fusion head, which significantly improves inference efficiency over the complex message passing neural network teachers. In addition, graph explicit neural network explicitly encodes the graph topology as an important source of information, which guarantees its effectiveness even with limited node features. Furthermore, our graph explicit neural network has natural interpretability by modulating relative importance of graph topology and features contributions to predictions via attention weights learned by our fusion head. We evaluate the performance of our GNN framework. We compare our method with MPNN teachers on the task of node classification. We report experimental results under both the transductive and inductive settings. Then, we adjust the ratio of the accessible node features to evaluate the generalization of graph learning models under limited node features. In addition, we visualize the distribution of attention weights to analyze whether GNN can learn appropriate attention weights on different datasets. Besides, we compare the inference efficiency of our GNN and other acceleration methods on the MPNN models. Last but not least, we conduct the ablation studies to analyze the effects of optimization targets and the fusion head. Our experimental settings closely follow those of the previous work to ensure a fair comparison. Under the supervision of the message passing neural network teacher GraphSage, our graph explicit neural network achieves more accurate and efficient inference than the teacher. On the left-hand side, we show the test accuracy in the y-axis of GraphSage and our graph explicit neural network on node classification of the Cora dataset with different ratios, which is x-axis of the accessible node features in terms of the input channels. On the right-hand side, we show the inference time for 10 random nodes in the OGB products dataset. We report the transductive node classification results in Table 2 and the inductive node classification performance in Table 3. Our graph explicit neural network outperforms all the baseline methods, including its teacher GraphSage and the advanced knowledge distillation method GLNN on the transductive and inductive node classification with 4 features. Under the challenging setting of limited features, the improvements achieved by our graph explicit neural network is much higher than those with the rich features as presented in Table 2. More experiments can be found in the paper. Thank you.